So people ask me why a guy with a perfectly good career in biochemistry got involved in population dynamics, and I said, because I saw the elephant in the room and I was frightened. It was overpopulation. I tried to bring it to the attention of others, but they would not look at it, or they would look at it and then they would just look away, but I kept looking, and now I teach a course in human population. So the most often cited models for the future of human population consider only the birth rate and the death rate and migration, but usually lack the constraints imposed by global resource limits. The paucity of dialogue on global limits within the mainstream economic reporting, even as it pervades the human ecology literature, represents nothing less than a failure of science communication. Predictions that fail to consider limits tend to be unrealistically optimistic and have contributed to widespread disavowal of overpopulation as a problem. A more realistic outlook for the future could spark social feedback effects that soften the catastrophe. The solution to this public education problem is to develop a model that is simple enough for all to understand and is built on good assumptions and fits real data. In this work, we have developed a dynamic system that incorporates global limits and retains simplicity as much as possible. The model consists of two closed systems that interact: land and mortality. It predicts that the global population will not follow the UN predictions, but will reach a carrying capacity and fall with it to an uncertain but low sustainable level. Take-home message: population will peak and decline soon. The sharpness of the predicted downturn is because population growth on Earth is like a fire in an enclosed space. It grows rapidly, consumes all of the oxygen, and extinguishes itself even more rapidly. Like a fire in an enclosed space, humanity is consuming nature, but cannot live without it. I hope you agree that the planet is a closed system. At no point in this talk will I consider the possibility of colonizing another planet. To start the modeling, we must first realize that human population growth over the last 1,000 years does not fit a simple exponential growth model. In fact, at first glance, it actually looks hyperbolic. In a 1960 effort to explain the data, a hyperbolic fit was taken seriously and shown to fit population going back 10,000 years. The asymptote of the hyperbola was dubbed doomsday and calculated to be November 13th, 2026. If we zoom in a little on this linearized hyperbola, it's a log-log plot, and log time goes to the left in this plot. Although the authors believed the population would level off at 4 billion by 1980, population continued to follow a hyperbolic fit for another 40 years up to 1999, when the population was 6 billion and fell about 500 million short of the hyperbola. This paper shows the power of simple curve fitting as compared to complex birth-death models to predict the future without bias. So I'm a fan of simple models. Simple, mind-sized models have many advantages. They're easier to understand, easy to teach, easy to manipulate, easy to fit to the data, and they're more likely to be robust and predict accurately into the future. So the point of this whole study is, can a simple model predict the future of human population? I believe the solution to the science communication failure that is the human population predictions of the UN is to present a simple system that cannot be easily denied, that reproduces past population growth, and which respects the finiteness of the Earth. Of course, this is not the first time systems dynamics has been used to deliver the bad news about population overshoot. Dana Meadows and others created version 3 of the world model in 2004. The results of the so-called standard run are shown on the front of the Limits to Growth book, the 30-year update, which, by the way, is the text for my course, Human Population. And they show carrying capacity dropping and followed by population. But World 3, as you can see on the left, has 16 stocks and over 100 variables. It's not a simple model. So over the last 3 years, working with my students in the course, I've been working to develop a new model dubbed World 4. And over this time, it has grown progressively simpler. In the first version of it, we had country modules, and it was not very simple at all, but it attempted to put all the stocks into closed systems. The next iteration of it, we had John Holdren's I equals PAT model for ecological impact, along with some other economic indicators, and it produced some kind of weird oscillating Lotka-Volterra style oscillations. The third iteration of it consisted of only 4 stocks, very simple model, and it did reproduce hyper-exponential growth of the population, and it did include technology. And but it did not have closed systems. That was followed by a model that did have closed systems and also incorporated the Holdren's I equals PAT and had land fertility in it. But this model, for some reason, always collapsed. What came after that was the model I'm going to talk about today, called World 4.5, but I'm just going to call it World 4. The model consists of 2 closed systems, 4 stocks and 4 flows, 11 variables that were fit to data. Of those, 8 variables were fit to single values, and 3 of them were fit to ranges. There are also 7 equation nodes and a few output variables and data, and I'm going to walk through it. All of this is on, it can be found in Insight Maker by searching for my name or World 4.5. So here's the model. It consists of 4 values, which are the starting values for the stocks. Some of those are from the literature. 3 of them were fit to the data. 5 variables that were fit to historical population data and fit to single values. 3 variables that were fit to ranges of uncertainty. And 7 equations that don't include any additional variables within them. There's also output nodes and historical population data for the purpose of fitting included there in the model. There are 2 submodels, subsystems within the system. There's a closed system for land that converts between human-occupied and wild land. Human-occupied called humans and the wild land called nature. And another system that is in the units of rate, of death rate, and this is a little confusing. We have a node called disease, which reflects the sum total of all modes of mortality for humans. And we have another node called technology, which consumes disease, and so therefore is measured in the same units, and technology is a suggested term for some things which do all they can to reduce mortality and increase lifespan. So that's and we're not the first to introduce the term technology into a system like this. Technology has been referred to before as something which grows intrinsically and has the effect of increasing lifespan, improving human existence, for lack of a better word. Now, the disease represents the mortality rate, as I just said. It's modeled as the rate of return of cultivated land to wild. And so because humans are modeled in a land-based model, rather than having that flow be death, it is rewilding, or the return of human-occupied land to nature. By including this type of model, what we've done is we have something called disease that is decreasing exponentially defining the flow from humans to nature, the death rate. And so what we have is an exponentially decreasing death rate, and that successfully reproduces hyper-exponential growth, which was what we see in the data. Here's the equation for hyper-exponential growth, if you can read it. It's an exponent within an exponent, and that little underlined part in red, that exponent is what we call technology, and that's an exponentially growing quantity. That is the exponential growth that is compounded by exponential growth of technology. That's the technology, I guess, compounds the exponential growth of humanity in a way that then produces hyper-exponential growth, super fast growth, almost hyperbolic. Then the disease is depleted by technology, and that is a function, an equation that has 4 variables, one of which was fit to a single value, but the other ones are sources of uncertainty in the model. Basically the take-home is you can consider technology the anti-mortality in this model, not the typical use of the term technology. Okay, now looking at how technology then returns to disease, because we have a closed system, we model that as the reemergence of disease through technological obsolescence caused by changes in the environment, modeled by the depletion of nature. That is, the depletion of nature creates an environment in which technology is made obsolescent, in which disease then can reemerge, or other forms of mortality can reemerge. Humans are modeled as a stock measured in global hectares, and so it's not so much humans as human impact, but that number, just like humans, grows intrinsically in proportion to itself and is subject to the availability of resources, which is nature. And humans die extrinsically at a rate that is exponentially decreasing, modeled by disease. Population is an output variable, not an input variable, so it's just a readout, and what it is that it's the quantity of land occupied by humans times the carrying capacity of that land. Carrying capacity itself is a function of 4 variables in 3 stalks. So lots of fitting had to be done. So all the parameters except the starting value for nature were fit to historical population data. N0, the starting value for nature, was derived from the literature, specifically the ecological footprint literature. So manual least squares curve fitting proceeded from variables affecting the distant past to variables affecting the present and future. So this is an animation of how that was done. First we start with the population data itself. We set the lowest level to be H0, the starting value for humanity, and introduce a simple exponential growth for most of the first 2,000 years of the model, and then we introduce hyper-exponential growth by the introduction of the technology factor. And now if we zoom in to just the last 100 years or so, hyper-exponential growth is then fit to the carrying capacity, and when we add an upper limit to our growth, it creates a downturn in the population. Optimizing the parameters for the carrying capacity fits the data points of the late 20th century and early 21st century. And then uncertainty projects into the future through variables that are that model the aggressiveness of the consumption of nature and the robustness of technology, and that determines the degree of the steepness of the collapse after the peak, and also the equilibrium population that follows that collapse. The values that are expressed as ranges for these uncertainty parameters are defined by the limits of that still allow accurate fitting of the late 20th century data. So this range reflects the numbers that don't affect the populations in the late 20th century, early 21st century. Okay, so that's how the model was created, and let's see what it produces. This is a plot now of population in red superimposed on historical population data, and you can see the fit is very good. In the dashed blue lines, you see the carrying capacity increasing due to the effect of technology in the 19th and 20th century, and then falling due to the depletion of ecosystem services in the 21st century, falling to an unknown level with a wide uncertainty, and population following the carrying capacity also falling to an unknown level with a wide uncertainty, but the uncertainty is very much on the low end. The high end of that prediction is maybe in the 2 to 3 billion, but the low end in the hundreds of millions. So how did that happen? Well, now we can look into the model and see if the mechanism for this result makes sense to us. And what I'm plotting here is nature, the wildland plotted in dotted lines, high, medium, and low scenarios, and those are just different options for settings of the three uncertain parameters. That collapse in nature that you see there is due to the expanse of humans, and since they grow exponentially, they consume natural land with exponential increase. And so what you see then is as technology goes up down here, contributing to the expansion of humans into all wild lands, the depletion of nature leads to a depletion of ecosystem services, which in turn leads to a loss in land productivity for domesticated land, leading to a loss in the carrying capacity, leading to a loss in the human population. So that's what's behind the peak and the decline of population. If we don't like that result, and I understand totally if you don't like that result, then what we should do is really look more deeply into the model and see if any parts of that don't make sense to us or some things that we might want to change. Here are three equations which are used to model the carrying capacity. And let me go through the three equations and then I'll show you what they look like when they're combined. The first one is a sigmoid curve and expresses the loss of ecosystem services and that it is nonlinear with the loss of nature. And here I'm evoking Paul Ehrlich's rivet popper story. I have it on the next slide. Paul Ehrlich opens his book, The Population Bomb, with this story. He says the ecosystem is an interdependent web of services, and it's interdependent to an unknown extent. Ehrlich's rivet popper pops rivets from the fuselage of an airplane, having no effect on its safety until the critical point where the fuselage ruptures in flight. So the rivet popper model is that ecosystems go to zero as nature approaches some unknown critical point. Above that critical point, ecosystem services are simply proportional to nature. That's a simple assumption. And at some point then, ecosystem services hit zero because, the fuselage of nature ruptured in flight because he popped out too many of those essential connections in the food web of life, to be a little poetic about it. Going back to these equations, the second component is that land is in a closed system. It's either natural land or domesticated land. And we would include land and sea in that, all the Earth's surface, expressed again in ecological footprint terms, global hectares. Technology is assumed to increase the productivity of cultivated land and sea up to an upper limit. This was an assumption, but it was also a necessary assumption I found in fitting 20th century population growth, that simply decreasing the birth rate exponentially wasn't enough to get the extreme steepness of what happened to us as a species in the 20th century. And so in addition to exponential decrease of the death rate, we had to have also exponential growth in the carrying capacity, and that also agrees with what we know about farm and cultivated land production, both in land and sea, especially in the second half of the 20th century. So since those biocapacity numbers are known, I fit the model to, in addition to population, also to the known increases in food production. So another, what I thought was a reasonable assumption is that the ability of technology to add to the carrying capacity should follow the law of diminishing returns. There should be some point at which we just can't push the land any farther. So it's modeled, and that number D was fit to population data in addition to food production data. So now, if we combine all three of these equations, we get a three-dimensional carrying capacity surface in the dimensions of the remaining natural land, technology here color encoded, and the readout being carrying capacity. So now if we look at what happened and where we are now in time, we're at a point in time where carrying capacity has been going up for the last 100 years, and occupied land, domesticated land, has also been going up. So both of those things have been driving human population up. But the losses of ecosystem services are now predicted to lower the carrying capacity dramatically. And while we will try to extract the resources we need from the ever-shrinking land and sea, that effort will further exacerbate the loss of the carrying capacity by destroying the remaining ecosystem services. And this is what the model predicts will happen. So if we take this three-dimensional surface of carrying capacity and then plot what the model says will be the carrying capacity with time, and here I'm plotting both carrying capacity and technology with time, what we see is that carrying capacity climbs up this three-dimensional surface in both technology and land use dimensions, and then it falls as land use increases due to both the loss of productivity and the loss of technology, the latter due to the emerging diseases and other forms of mortality as technology for survival becomes obsolescent in a rapidly changing world. So it doesn't sound good. Here's sort of the feedback effects that we see to help you make sense of this. Increase in technology leads to more farming. More farming leads to higher carrying capacity. Higher carrying capacity leads to higher population. Higher population leads to the loss of nature, natural land, which in turn leads to lower ecosystem services, which in turn leads to lower carrying capacity, leading to lower population, and then leading to a gain of nature, leading to increased ecosystem services, and you can see how this is a cycle. So, however, we don't actually observe oscillating behavior in this model. It bounces up, and then it sort of equilibrates. Okay, so if we now do the fit and we look at this data, this is the 20th century observed population data for the whole globe. If we now do the fit and we adhere to that 20th century data tightly, then the inflection point of the curve should be placed in the period between 1990 and today, and this places the peak in the near future. Using the three parameters that govern the future scenarios, we then get a narrow range of possible futures, which I could show you here. And the narrowness of that range is because setting any one of those parameters outside of its narrow range will not fit the 20th century and the early 21st century population data. So we are then forced to conclude that in the future we will peak at somewhere between 8 and 9 billion, and will happen somewhere between 2028 and 2038. Most likely around 2033, and most likely around 8.5 billion. Those uncertainty parameters we can look at now. This is population carrying capacity and also nature as a function of the three parameters that are not very well defined by the FIT. They're defined within narrow ranges. The parameter called A is Paul Ehrlich's rivet popper model, and carrying capacity goes to zero before all of nature is consumed. And there's still rivets in the fuselage when it finally fails. So the rivet popper model value A is the inflection point of this curve that expresses carrying capacity as a function of remaining natural land. The parameter U is the aggressiveness of extraction of natural resources. More aggressive extraction leads to a lower population in the model. And then the variable V models the obsolescence of technology and the emergence of new forms of mortality due to the depletion of nature. The robustness of technology, it turns out, creates a steeper and deeper collapse. And this is counterintuitive. Let me say it again. More robust technology leads to a more severe population collapse. So now we can compare this prediction to that of World 3, Dana Meadows' model, and which predicted a later and higher peak population, you see here in blue. These three plots were run in InsightMaker using different settings for the maximum amount of arable land in the model. And so you can see neither of these models looks anything like what the vast majority of us have come to believe is our population future, and that's on the superposed UN model right there. Now, what you choose to believe is up to you, of course, but at least I hope that you are somewhat influenced by systems dynamics. If you don't like what you see, and you don't want to believe that we are doomed as a species, I totally understand, and I don't take any offense. Then the best way to question the model is to first question the assumptions that went into it. So here are the main simplifying assumptions. One stock for all humans. Population cannot exceed the carrying capacity. The carrying capacity is proportional to wilderness, and no free will. So let me take those one at a time, because I think maybe we can find some flaws in this model. I hope we can. I don't like the future that this model presents. So one stock for humans. Can we justify that? Maybe we can. If you think about the way that humanity is divided up in models, economic models. I call them that because they come out of economics departments. One way is by regionality. But if there's hardship somewhere and there's a possibility of migration, people are going to move where there's less hardship. And if you assume that the migration rate is faster than the growth rate, then what it creates is essentially a self-leveling system, or one pool. So if that's a reasonable assumption, it justifies dealing with population using a single stock for humans. Another way that humans are divided up into subclasses is by age demographics, and this is done both in the economics models and in World 3. And I would argue that it's not really necessary to divide up the population by age, because the shape of that demographic pyramid is the result of the growth rate, not the cause of the growth rate. We're already modeling the growth rate in the model, so I don't think we really need to have the details of the age breakdown. So now I would say humans are one stock for now. But we want to think about it, because as things get bad, what's going to happen to humanity? Do you think, yeah, possibly humanity will divide up, and what we'll see is intraspecific conflict. Intraspecific, you know that word, that means within a species. So if divisions are deep enough, we could produce a different kind of downward spiral. And I think that's one of the principal ways in which this model is probably flawed. I really want it to be flawed. Another assumption is population cannot exceed the carrying capacity. Is that justified? Well, maybe stored food can be used to allow population to exceed the carrying capacity, but that would just be temporary, and in practice it's not going to have very much effect on the outcome of the model. No one survives for long without food and water. So I'm not backing off on that one. I'm going to say population cannot exceed the carrying capacity long enough to make a difference. The third simplifying assumption is that the carrying capacity is proportional to wilderness. And now this one might not be so intuitive, but if you think about it, nature provides ecosystem services that we need to survive, and those ecosystem services are proportional to how much ecosystem there is. Typical examples of ecosystem services are temperature control, climate stability, keeping the conditions for crop growth within a comfortable range, and getting outside of that range is going to affect the yield of the fruits and grains that we need to survive. pH of the ocean is going to be controlled by ecosystem services. If we go outside a certain range, we're going to see a die-off of the fish we need for our diets. Protection from UV radiation, the ozone layer, if we deplete that, we're going to see an increased death rate by cancer. Absorption of waste and pollution, oxygen generation by plants, CO2 fixation by plants, which ties into temperature control to the climate. All these things are services that the ecosystems of the earth provide for us. I call them services because what they do enables us to have the high carrying capacity that we currently enjoy. Now, all these ecosystem services depend on the presence, quantity, and quality of ecosystems, which themselves are a function of the biodiversity of those ecosystems. So the biocapacity of an ecosystem depends on how robust it is, which is affected by the degree of biodiversity. Again, I keep thinking back to Paul Ehrlich's rivet popper model. We don't know what species, that we've driven into extinction is going to finally be the straw that breaks the camel's back, or the rivet that ruptures the fuselage. So carrying capacity is proportional to wild systems in probably a very non-linear way. The other way is that ecosystems are self-regenerating, and that regeneration is proportional to the current amount of biological activity in the ecosystem, which is true of any living thing. It grows in proportion to its own biomass. And we should remind ourselves that humans do not currently take on these ecosystem services as our own responsibilities, which will get me to the next argument in a minute. So the third simplifying assumption is carrying capacity is proportional to ecosystem to wilderness. Where is it? There it is. Anybody remember Biosphere 2, how 8 humans lived in the biosphere for 2 years, and then the atmosphere went bad and they had to leave. So I would argue that I don't think we really can substitute human engineering for the world's ecosystem services. If we can't get a small biosphere to be stable for 2 years, I really doubt that we could engineer the entire planet. So final assumption is humans have no free will. The reason I'm going to argue that is two or threefold. First, business as usual models are typically the right ones. When we start second guessing the model and saying, yeah, but maybe if we do this, we'll have some better outcome, some outcome that we prefer in our future, then we're usually wrong. And an example of that is the doomsday model, the hyperbolic fit to population in 1960. They assumed they were wrong, and they thought, oh yeah, it can't be that simple. I'm going to second guess it. I'm going to say we're going to level off in 1980. Didn't happen. The doomsday model continued to predict population almost through to 2000. Second, humans are like animals. We're hopeful. We think that we are not like animals, but David Pimentel and Russell Hoffenberg have published a nice paper documenting how human populations have risen to the level of the carrying capacity, risen to the level of the food supply, much like other animals do. It's sort of a biological instinct to do so, and we are rather arrogant to think that we're not subject to the same laws as other animals. And third, allowing for free will is like allowing for denial. Saying, here's this model, but, you know, I hope, and then just, it's an out, it's an escape. So what good is a predictive model if then I give you an escape from it? So I would assume not free will. So that's the model. If you're not already depressed by this news, I can kind of bring it home with this little hand-drawn graph. Here it is. So consider the life expectancy today if we accept that population will decline starting in 2033 with a 10 to 15 year half-life. A child born today, therefore, has a median life expectancy of about 25 years. And the median age of a child born in 2050 will most likely not even see their first birthday. More than half children born by that date. In order to fit the model, more than half of children born in that year will die in infancy. So yes, the UN life expectancy projections are rosier, and I would totally understand it if you choose to put those numbers into your retirement calculations and not my numbers. I sincerely hope that I'm wrong. I've dedicated my life to the education of young people whom I hope will go forth and earn a good living for a long time in peace. But to hedge my bets, my lab has secured funding to develop a contraceptive vaccine, and with it we hope to undercut some of the runaway growth and maybe soften the fall a bit. So thank you for listening. If you liked what you heard for some unfathomable and perverse reason, then please look for this video on YouTube. You can search for my name or Humans versus Nature.